All right, it's exactly 2 o'clock, so let's get started. I have to run out from this session. Right on time because I'm on the panel in the next session in the other room. So I'll leave questions to the end, but I am keen to hear your questions. And then can everybody hear me okay? This volume's all right? All right, great. So thanks for coming. I'll be talking about using containers for HPC. So the focus of this talk is like, what are containers and how can I write my own one and some best practices. It doesn't, so it's aimed more at like the researcher perspective as opposed to a sysadmin perspective. So if you want to have a chat afterwards of like, I'm more of a sysadmin type of person, how does Pawsey use containers to support their users as opposed to how do I use containers as a researcher, happy to have a chat. So I work at the Pawsey Supercomputing Research Centre in Perth, Western Australia. I'm a life sciences supercomputing specialist, so I work to support biological researchers primarily. I have a background in neurogenetics, so a little bit different to some of the other domains here, but it's been really great working in HPC. So Photonics is our supercomputer. It was 4th greenest in the world. It's now, I think, 10th. So we should update this slide, but it's still hanging on to the glory days. So this is 30 times more powerful than our former HPC systems. And as Macho mentioned yesterday, Photonics is the genus name for quokka. And you'll see some of those in the panel presentation coming up. So we have a lot of interesting architecture going on. So we have the supercomputer. We also have our Nimbus cloud. We have a really large Ceph object storage system called Acacia. So users really like that, and a really fast internal interconnect. So as an overview of containers. So, what can you even use containers for? Like, what's kind of the point of them? So there's lots of different sort of use cases, like avoiding local installation of packages. So for example, conda, pipt, apt-get. You can't necessarily do that on HPC, or you can't necessarily do it well. So for example, we have a lot of users that like using conda for their complex, bioinformatics tools, for example, with a complex dependency tree, but it can break the inode quota, and so that's a problem. Something else that is really nice is for handling clashing or multiple versions. Again, this is really relevant for something like bioinformatics because they always have this huge software stack. Shipping software that you've published. So if you are creating something that requires a very specific sort of environment to operate in, and you want to share it with someone, containers are really great for that because you can literally push it to a repo, they can download it, and they can run it regardless of what's going on their system. Something else that we really like for in terms of reproducibility is fitting in with workflow managers such as like Nextflow, SnakeMake, Airflow. So do you guys use any of these type of workflow managers? Is this a new concept or? Okay. So if you have complex workflows, so you're not just using one bit of software to process everything, maybe you have multiple steps chained together, you can use these things called workflow managers to handle that for you. And so it has resume capability, it locks down all the versions for you, it tells you what has run successfully, what has failed, you can restart. And so they're really big in bioinformatics because they do have these complex workflows. You might use 10 different bits of software in a simple pipeline. But it seems increasingly, even feels like radio astronomy needs something like this. So just try to bring it to people's attention that it's something to think about. It will make your life a lot easier if you do have these complex workflows, particularly with containers. It's really a nice combination. And something that we've used containers for a lot as sort of sysadmins is for bleeding edge versions that wouldn't work bare metal. So we have an AMD, like a HPE Cray X system with AMD GPUs, and getting the newest versions of ROCm on as like a system-wide install has been very challenging. But with a container, you can actually have the newest versions of things. So we wouldn't have been able to do that with a bare metal install. And again, it's kind of some good use cases. So if you have a large volume of software to be installed, containers can save you a lot of time because you just download and run generally. If you have complex builds with lots of dependencies, again, like these deep learning frameworks or bioinformatics, even things with, huge dependency trees, like with Python. So you can having like a single container file can actually improve the performance on a parallel file system. And something else I'll talk about in a bit more detail is if you have like this intensive I/O patterns in software that write a lot of small files, for example, OpenFOAM, not just OpenFOAM, but those types of things. A single container file can improve performance of parallel file systems, and it also stops you from breaking luster, so that's a big benefit. So I feel like this crowd probably is already fairly familiar with how programs run. So at the top here, these are different programs, and they share, libraries, dependencies, and the operating system. And so that's fine if you're not running too many different things. But you may get into dependency hell. Not ideal, and can be very frustrating. So with containers, what was previously a sort of shared environment become these self-contained environments. So a container encapsulates everything you need for the software to run. And so this runs independently from the host machine on your, laptop or cluster. So this means that, all these libraries and dependencies are different or separate. So just to really drive the point home, these containers encapsulate everything you need for the software to run. So the environment variables, the installation commands, the libraries, dependencies, but you can also get them to talk to, the system versions of things. Like, for example, if you want to run NPI with a container, you can dynamically link that with the system NPI with some hacks. So this is actually I don't know if you call it a sculpture, artwork in Fremantle in Western Australia. So these shipping containers. Very exciting, I know. So with containers, you can get workflows that are reproducible, robust, very important, portable, which is always nice, and a lot easier to maintain. So it saves you coming back and cursing your previous self for not keeping good notes or good comments or what did I do 6 months ago, which happens to all of us, I think. So in terms of reproducibility, I do think in trying to install someone else's software is a little bit like trying to assemble an IKEA piece of furniture. In theory, it's simple. IKEA tells you this is fine and you can do it. And then you get home and you're like, what is going on? So it's a really big thing in biomedical research to have reproducibility, and it's not necessarily done very well, but it's a focus, particularly with like human research. So you want to be able to have repeated analysis giving you identical results. So this is both for you and your own, like maybe you have a cohort of cancer samples and you're getting them through in batches as, patients get treated. And so you don't want to have these batch effects because you couldn't remember which version of R you used. You need to make sure it is locked down and you're going to get exactly the same identical results, and it's not going to be, skewing your analyses. And also this robustness. So with a container, you lock down these identical tool versions over time and your container won't suddenly break. And so again, with this portability, kind of the same thing. Everything is locked down. You can send it to other people. And also you're scaling up from your laptop to a different, to HPC, or you're, moving between different HPC systems. You don't need to reinstall, recompile, all of that every time you move. You can just literally download from your own repo and run, which is like fantastic, saves you so much time. And also increasingly important for scientific publishing, that other people can run your code, or the reviewer can run your code. I can't tell you the number of times I've tried to use someone else's bit of like bioinformatics software and just the installation is so terrible that it's like, I can't even use this. And so you can't even, they're not going to get a lot of citations if no one can use their thing, right? And, easier to maintain. You use one recipe to sort of rule them all, use it everywhere. And leaves you time to do other more interesting things. So again, this is talking about the workflow engine. So with for example, Nextflow pipeline, you can write code in any language. Nextflow wraps around that and will orchestrate all of your tasks. It will talk to Slurm or PBS, or you can run in local mode on like one node. And then you can define your software dependencies via containers or Conda or modules as well. Yeah, and you can run it on all these different platforms. So just a bit of a spruik for that because it might make your life a lot easier. So that's like the really high level overview. In short, containers are good, would be the TLDR. So how do you actually sort of use them? So there are some container keywords. I'm just outlining them here so that we can kind of know what they're about as we talk through how to write and use containers. So a recipe is sort of the instructions for making a container. So you write down all of the install commands and then you build that, so which is kind of like compiling, which creates an image. And so that's a container, but it's not currently running, and that's what you ship around. So we'll go, this is just like really quick intro, and we'll go into more detail. And so, you know, the image might be a few gigs, which you can then place on a repository, such as Docker Hub or key.io. There's lots of them around, and they can be stored and shared there. A container is just a running instantiation of an image. So the image is, you know, what you send to your collaborator. When they run it, it's a container. You can kind of use the two words interchangeably, but if we're going to be correct for the sake of teaching, they are slightly different. And a container engine is software that allows you to run the container. So it allows it to come alive. So you don't talk to the container directly, you go through this container engine software. So this is a little bit more blurry than it was on my own laptop. But so this is actually what a recipe looks like. And typically you'll write your container recipes in the Docker format. That's become the de facto standard. So if someone says, I'll send you my Docker file, they mean the recipe, same thing. And it has just some specific syntax around all of your installation commands, which we'll go through in more detail. Then with either Docker or Singularity, you can build this, which then becomes these images hosted on this repo. So for example, these are all PyTorch images. And you have tags to indicate like the version, so maybe like the version of PyTorch, but also other info, like is it Rockham PyTorch, is it CUDA PyTorch, you know, these types of things you can specify in the tag, so you can get a lot of granularity. And so with this container engine, so Docker is a container engine, so is Singularity. So you as a user issue a command to either Docker or Singularity or whichever one you choose. Those are kind of the two most popular ones, which then executes the task. So Docker was kind of the first big one on the scene, but you need sudo to kind of do anything in Docker, so it's not very good for HPC. So you'll typically write your recipe file in like the sort of Docker syntax, but for example at Pawsey we use Singularity extensively. There's also Shifter, Charlie Cloud, Podman, so it really depends on like what system, what your sysadmins are keen on, and they all kind of do the same thing. But the good thing about all these other ones apart from Docker is you don't need sudo to run, so you don't have elevated privileges inside the container, so it means that you can actually do it. So when you're running a container, actually the file system is read-only. So you can't just write things into the container on the fly once you've built it. So you can execute and you can get the container to write things to the host system, but by default you can't write into the container. And so the sort of file system or the file type with Singularity is a squashfs or CIF file, which is actually quite performant on parallel file systems, so that's also quite handy. And then just some general user-friendly features. You have the same user as in the host, so if you're running it as like Beecroft, that'll be also the user in the container. In general, you have the same working directory as in the host by default, so if you're in, you know, Scratch Project 01, that'll be the same. And in general, the shell variables are inherited from the host. So you can set some environment variables and they will, in general, be inherited by the container, but you do have control over that. So you can set or ignore variables as you like. So looking at some key commands. So again, this is this sort of singularity syntax. So if you want to pull a container from the internet, from a Docker registry, it's actually very straightforward with this singularity pull. So you provide a little bit of the syntax with, you always have to put Docker in front if it's a Docker recipe, and you give it the name of the registry, the name of the repo, and the tag. So if we look sort of here, you would give it this, like for example, PyTorch, CUDA NN tag information. So you can see what this kind of is down here. And so on all the repos, it'll generate for you what tag information you require. So you don't need to know that yourself. You can look it up. And so that will download this CIF file to your host. Then if you want to actually execute something with the container, so for example, maybe you have like a Python container, you want to use that to, create a graph, do some machine learning. It's actually relatively straightforward with just this singularity exec. You tell it the name of the container that you want to use, and then your command. And something else that's really useful if you are if you are trying to debug a container. So sometimes, you'll get something from someone and you're like, what have you actually done in here? You can shell into the container and basically like open a terminal inside there. And then you can like poke around. And so, did they put the application in /app? Did they put it in like user bin? Did they put it somewhere really weird? Sometimes the only way to know is to shell into it and just look around. So I find that quite useful. You can also use GPU-enabled containers by adding these flags, NV or for NVIDIA or ROCm. That said, though, we have found that using this ROCm flag on our system sometimes isn't actually very helpful. It can introduce some weird behavior. So if you have an AMD system, use that ROCm flag at your own risk. Try maybe with and without and see how it goes for you. I tend to not use it, but it is there. So here's like an example of how it would actually look. So on the system, for example, if I run burp Python 3 and see what version do I have, it's 3.6.13, right? But then if I cd into my Scratch and I load the Singularity module that we have on Zetonix, well, this is very old, but the one that we had when we made this training, then I pull this particular Python version, right? So it's Python 3.9, and so it'll tell me that it's downloading and converting to CIF format, starting the build, creating the CIF file. Usually takes like anywhere from a few seconds to a few minutes, depending on the size of the container file or the CIF file. And then if I do this execute command, singularity exec, the name of the container, Python 3 version, it's a different version to what's on the host. So I'm now enabled to use this different Python version. So talking about these environment variables, so sometimes you do want to isolate the environment and not inherit anything, so you can set that up. It's quite flexible. Or you might want to export some particular values, so you can also do that, which is quite nice. So there's lots of documentation online for, what was exactly that flag again, or, where can I find this particular thing, or how do I set various bits and pieces. The documentation is actually really quite nice, which isn't always the case, but this one is pretty good. And so one of the questions I tend to get from users is like, oh, well, I don't want to write my own container. Like, do you realize how busy I am? That's a lot to ask, which is fair. But almost always there will be a container recipe already out there that'll do what you need to do, or get you most of the way. And so there's this Docker Hub, biocontainers if you're a bioinformatician. Key.io is also good. NVIDIA has their own container repo. AMD also has a sort of AMD ROCm container repo as well. So you can have a look at any of those. And you don't even have to have an account to pull the containers, which is also handy. If you pull too too many containers too frequently from Docker Hub, though, they will start charging you. So just be careful about that. Don't be pinging the database like hundreds of times. You might get a bill or a nasty email or something. Okay, so let's have a quick look at the Docker-specific sort of keywords for writing your own container, right? So always you start with this from image. So the image it might just be like Ubuntu 22, or it might be an image that you have previously made. Like at Pawsey, we have a lot of images that we have created because we need to have a rock conversion. We want to have MPI that works in Singularity, or we have this particular setup for PyTorch or TensorFlow, and so we have those as our base containers. But you can also just get generic ones. So, for example, Python or Conda, all sorts of different sort of base images. And then when you're running your installation commands, it's very similar to how you would normally do, basically, if you imagine you're starting from like a fresh VM or something and you need to have, sometimes you might need to install really simple things like curl or wget, all the way through to like fairly complex system dependencies. You, of course, need to sometimes define some shell variables. So for here, this is like our actual PyTorch Docker file that we use, put together by my colleague. And so you can see here, hopefully, it is a little bit blurry, I think. So he's pulling from our Rockham and Pitch container. He's setting a bunch of these environment variables. He's running, like he's installing, I can't even make it out, sorry, but installing a bunch of these things in one layer, and then git cloning various things. You can also add and copy files from the host to the image. So sometimes you might have like a YAML file that you need included, or even like sometimes small bits of data that you want to make sure are in the container. You can do that. And so you would, once you've finished your recipe, you'd build it with like Docker build, put in a tag, and specify any files that you want to go in there. So it's usually like Docker build, Docker file, creatively named, and it'll work its way through. And then it'll tell you also if like the build doesn't work for any reason. So if you're missing a dependency, or you can't get a version, or you've forgotten to install Git before doing git clone, it'll give you an error and you can fix it and then try again with the build. Oops. And so as I said before, by default, the container is not writable, but you can actually share files with the host machine doing this thing called bind mounting. So it's pretty straightforward. You can bind multiple directories. You can also put in, if you need to, these specific paths into the container. So here's a real example from some bit of bioinformatics software. So Singularity exec bind, this capital B. So I'm binding wherever my inputs are into this very particular directory that InterpreScan needs to be in this directory for bioinformatics reasons. And so now the container will know this thing inside the container is actually InterpreScan/data. And then I'm executing this InterpreScan.sh. Does that make sense so far, or are we a bit lost? Yes. Yeah, so typically when you have the container, you can't by default read or write anything. You can't write anything to the container. So if you're like doing some analysis and you're writing an output file, where can you write the file? Well, or if also you maybe need to read some files from somewhere that's, not in your present working directory, maybe it's, some scratch slash references or somewhere else, you can make sure that Singularity can read and write to these directories that you need by bind mounting them. And so you're basically saying, I want to be able to, Singularity, I want you to read and write from these particular directories. So in this case, so you can either simply just make them available. So dir1, dir2, dir3 will just be available to the container. Or you can specifically map your whatever local directory you have to a specific path in the container. So it's kind of like symlinking it, I suppose. So if I want to, if all my inputs are in this inputs folder, but for some reason the container needs to think that they're in interpret/scan/data, I can do that with this syntax where I have bind mounting and then a colon in the middle, sort of source and destination. Does that make more sense?
Yeah, so what I've seen in the past is that sometimes they're able to input the directives in the Docker file, so like chmod. Is that similar to what you're saying?
I think this is slightly different because it's at the runtime. And you can change it on the fly. So yeah, it is a little bit different. Any other? Yes. Yeah, so if it's trying to write something to disk and you haven't allowed it to write to disk, then you'll get some sort of error. If it's just holding it all in memory, then that's fine. Typically by default though, like when we have like the way that we've configured things on Sotonix, for example, like there's already some automatic bind mounting that we've like done in the background for you. And so I say this because, obviously you can't know what other sysadmins have set up, but a lot of the time, if they're supporting you using containers, they've probably done some like quality of life improvement so you can read and write automatically to your present working directory, which does make life a lot easier. I do, sometimes forget to do that if I'm working somewhere else. I'm like, what is this problem? Oh yeah, it's not all nicely done for me in the background. So any more questions? It feels like a long time to just be talking and not letting you ask anything. Seems a bit unfair. All good? Okay, well, keep going. So something else cool that you can do with containers is something called a persistent overlay. And so this, hopefully you can see this. I really like this comic because this is what happens every time someone comes over to my house. So friends arriving soon, like, let us store our irregular shapes inside shapes with flat surfaces. So the friends arrive and say, your home is beautiful. And they say, thank you, we own things, but we have hidden them. Which is a bit like, madly putting everything away into the cupboard or hiding things in your cabinet before people come over. And you can kind of do the same thing with this persistent overlay. So if you have something like OpenFOAM that's writing like, thousands and thousands up to like millions of files, that's going to break luster. You're going to go over your inode quota if you have one. So like for us, I think it's 1 million files per user. You can easily go over that running OpenFOAM. And so we have that quota enforced so that it doesn't crash Scratch, which has happened before. And so with the singularity overlay, you can create with SquashFS this what looks like just one file to luster. And so it's a bit like you have all of these different files kind of scattered everywhere and you manage to put them all inside your filing cabinet. That's kind of like the equivalent thing with what you're doing with this overlay. So everything gets written into this overlay, which you can access with your Singularity container, but it doesn't put the same stress on the luster file system. So it's more like, so to go through how one does that, so first of all, you create a directory for the overlay on the host system, so making this directory here. And then I'm creating this overlay of just 500 megs of empty space. And I'm saying I want to put it on this overlay directory that I've already just made. And then, for example, here, I'm doing Singularity Shell, mounting this overlay, making it available to the container, and then I can read and write into this overlay that I've made using this, ubuntu.cif file. So for example, if I'm like, I want to do this Conda installation, it's going to write loads and loads of files. I don't want to put that on Luster because I'm already at the top of my quota and I'm going to break everything, get a nasty email from the sysadmins. What I can do instead is put them all into this overlay.image file. So it's putting it all into this virtual file system with SquashFS. Does that make sense? Not really? Yeah? Yeah, that is correct. You can't write them in parallel. So it's good if you have just like one process. But for example, there was one user I was trying to help with this and got her to do all of that, and then realized, I wasn't super familiar with the software, right? Then realized it was actually trying to do parallel IO on this, and it doesn't work. So not for that, but if you're just doing something relatively straightforward with that parallel IO, it's a nice way to just kind of cram everything. It makes me think of IKEA, right? You know how they advertise these storage solutions, and it's basically like you just close the cupboard door on it and it's in there, but you're not going to look at it too hard. It's a bit like that, hiding it from luster. Any more questions on that? No? So I've also got some best practices for you, or just like a bit more information. So one question that we get is like, oh, okay, well, you really like containers. That's good. Should I put just all of my software into one big container? And like, yes, you can do that, but the kind of best practice is not to do that, because then every time you want to update one thing, you've got to rebuild the whole container, which can be annoying and time-consuming. And you're also starting to edge towards this dependency hell again. So it can be tempting to put everything in one container, and I'm sure there's some use cases where that's probably the best thing to do. But in general, we suggest that you have your containers to be modular. So then you can swap components in and out of your workflow as you need to. Or, out of your environment. You can keep tools isolated, and then you only need to edit one component as you need something else, right? Something that's actually quite an important concept just in general, so that you can write good containers that don't take up like 50 gigs, is that each instruction in your recipe becomes a layer in the container. So when I have, for example here, this from base image, Ubuntu, and then I'm running, getting an update, doing some build essential updates, and then I'm, copying in this make file, setting my work directory, I'm, compiling. Each of these becomes its own layer in the Docker file. And so with this, something like this is very minimal, and that's fine. But sometimes, you have these really quite long, complex recipes. They can be, 50, tens to sometimes hundreds of lines long, depending on all the stuff that you've got going on in there. And so if you're not very careful to clean up after yourself and put all of these layers, condense all the layers a bit, you can end up with massive containers. And so I've done this myself, where I've been just developing something and I've been a bit lazy. And I'm like, oh God, this is like 25 gigs. I do just even some really minor cleaning up, and it like shrinks the size by like a third to a half. So it's actually quite significant. I was really surprised at how much of a difference it made. So the best practice that comes out of that is combining your run commands as much as possible to reduce the layer size. So here on the top is kind of not the best practice, where you have each thing separately. So I'm doing a wget, I'm unzipping the file I got, I'm cding into the thing and doing make install, then I'm removing the file that I made. Well, that's good, or the file that I downloaded. However, you can actually put all of this into one run command with just some ampersands, and then the difference in size in this would be really significant, which feels silly in some ways. Like, why would it make such a big difference? But yeah, there's articles online explaining a bit further kind of the guts of why it is like that. But in general, Docker doesn't clean up anything, so you really need to work at keeping your images small just to make your own life easier. And also, removing files that you downloaded, or if you're using Conda or pip. For pip in particular, no cache dir, very important. For Conda, cleaning up afterwards with like Conda clean AF, those types of things, and removing, files that you don't need after a compilation. The other thing is that there is a build cache with Docker. So if you get halfway through building something, or say you build your whole container and it works, and then you're like, oh, actually, I need to change this version of something. Docker will only, when you go to rebuild, anything that hasn't changed, it'll just take from the cache. And so then it's like, takes 2 seconds, those layers. So if you have something that is put the most expensive steps at the top, because if they're not likely to be changing very often, you just want to pull them from the cache. If you have things that are frequently changing, like, you're trying to, does this version of Python work? Does this version of ROCm work? Put those more towards the end, because then top layers will just be pulled from the cache, and only the bottom layers need to be changed. And so that saves you a lot of time. Even if you just update like an environment variable near the top, the whole thing, everything afterwards needs to be rebuilt. And so can be annoying. So keep that in mind. The other thing is, where possible, being really pedantic about version tags. And so by default, you can have the latest tag on a lot of containers. And so if I just pull Python latest, well, what version am I getting? I don't know. Whatever happens to be the latest on that day when I'm building the container. But next week, it could be a totally different version. And in a year's time, it's going to be very different again. And so maybe all of my dependencies, that I've installed after that, relying on this Python version, will break. So actually, the best thing, if possible, is to specify the tag. So 3.7 or ROCm mpitch Ubuntu 22, or in as much detail as possible. Something else that you can do if you're doing lots of containers, and this is what we've done at Pawsey, is you can create a base image yourself that has stuff that you need in it that isn't going to change too frequently. Then you can tag that base image with a version, put it on your repo, and you can pull from that. So it makes it easier to freeze all the dependencies and avoid accidental updates. And again, this is, quite blurry, but this is the example that we've got here. So we have this build ROCm mpitch base Docker file, which we've made. And then if we want to make PyTorch, we're actually pulling from this Docker file. So this gets built, and then we import it with this from command and build PyTorch on top. Sorry, just have a quick drink. Also, where possible, use trusted images. So, like with anything that you're getting from the internet, whether it's software or, nobody torrents anymore, but kind of a similar analogy. Try to look for something with a high star rating on the repo. Try to look for something that's had a lot of downloads, so that that it's, from a legitimate source. It's not someone that's going to try and mine cryptocurrency from your container or something. Has happened. And so, this foobar Python, who is that? If you can get it from the official image from the Python Foundation or from Pawsey or something like this, we're not going to try and mine cryptocurrency on you. And also using version dependencies. So if you have, particular branch or even a commit hash or something like this, which is probably just good software installation kind of practice anyway, but something to think about. And so you can use these ampersands. You can use semicolons instead of ampersands, but it does make it a little bit harder to read. So, that's really just being picky. But if you want to make your container a bit more readable, or your recipe a bit more readable to other people, use these ampersands. Okay, so that's kind of the end of that. Do you have more questions? Yes, at the back. It's not so much using multiple containers. It's more you have, you have a sort of base image that you're using rather than importing multiple. So the idea, I think, was more that you have lots of individual containers rather than. Yeah. So for example, it depends on the shape of your workflow. So if with bioinformatics, you'll have 10 different steps which all have their own software, and they're all quite separate. And so for that, you could, in theory, have just one container which has everything, but best not probably to do that. You have 10 different containers for 10 different applications. Any more questions before we all run off upstairs? No? All right, well, thank you very much. I hope that was enlightening. Please do get in touch if you want to talk further with Marche or myself.